Good morning, students. So today we'll continue the week. So in the last class, we started Rutherford's alpha ray scattering experiment, right? So Rutherford's alpha ray scattering experiment. And in the last class, we have seen the oil drop experiment, how to calculate the charge, magnitude of the charge. And then we started Rutherford's alpha ray scattering experiment. So Rutherford alone, he didn't do. Why to give his name alone? Okay. So he alone, he didn't do that alpha ray scattering experiment with his colleagues called Geiger and Marsden. So most of the credit has to be given to these both. He is just a guide. Rutherford is just a guide for that experiment. So who did majorly is Geiger and Marsden. So these two scientists did most of the experiments and he guided, right? So Geiger and some NCRT or some textbooks, they will write it as, instead of writing Rutherford's experiment, they will write it as Geiger and Marsden experiment. In essence, that is also alpha ray scattering experiment only. Okay, a small revision, then we'll go back to the observations and all. Okay, so what we can set a source. I won't draw the complete diagram, try to see. Okay, so just a rough diagram. Okay, so can I set a source? From this source, what will happen? Alpha particles are coming out. Right, these alpha particles are sent through a small gap which is made by whom? Made by the lead bricks. Right, so these alpha particles are being strike and they are going and they strike the gold foil. So why only gold and all? I think we have seen in the last class. Okay, so strike the gold foil, which is of one layer. One layer of atoms are there. So no, that is very important. One layer of atoms are there, and alpha particle went and strike. Strike in the sense, what happened? Today we have to discuss. What happened after striking? So some of the alpha particles are bent without deviation. Take a question, very important. For example, some 10,000 alpha particles are going towards the gold foil. 10,000 alpha particles. So what these scientists observe in that most of the alpha particles went undeviated. Try to understand the point. So an atom is there, assume a gold atom, right? So some 10,000 alpha particles we have sent to that gold atom. I am considering only one atom. Okay, so 10,000. So what happened to the 10,000? Most of the alpha particles went undeviated. This is fast moving alpha particles, right? So they went and they went from inside and they came outside. Oh, very good. Is that clear? So went and it came outside without any deviation. So why they should deviate? Think about that. Why they should deviate? In a sense, for the atom, now we know inside nucleus is there. So nucleus is also positive. Alpha particles are also positive. Some deflection should be there. But most of the alpha particles, what they said, they went it as undeviated. First observation, what they did. Right? So observations. Okay. So first one. Most of the alpha particles went undeviated. Most of the alpha particles went undeviated while crossing that gold foil. Just I have written went undeviated. Where? While crossing that gold foil. Right? So 10,000 alpha particles came and struck here. Then what happened? Most of the alpha particles went undeviated. Very less amount of the alpha particles are deviated. So here a circular scale we can say, right? So a circular screen, which is zinc sulfide screen, right? So most of the alpha particles went undeviated and some amount of the alpha particles deviated. Why they deviated, we will discuss. Some amount of the alpha particles deviated. Most of the alpha particles undeviated. Some amount of the particles are deviated. So, how many number of particles deviated? According to the experiment, 0.14% of the total alpha particles. The total alpha particles, 0.14% of the total alpha particles deviated. Remaining percentage, all the alpha particles went undeviated. Right? So alpha particles came, most of them went undeviated. Only some 0.14, very less amount of the percentage. What happened? They deviated. Okay. So now what they thought is, okay, some are deviating, we'll count them. So here we have a circular screen, so we can go with a microscope. Here we can take a round and we can see how many alpha particles are deviating. They did that experiment and they found one alpha particle, one out of 8,000 alpha particles, one out of 8,000 alpha particles deviated greater than 1 degree. Greater than 1 degree. 1 degree. Okay. So most of the alpha particles went and deviated. 0.14% of alpha particles deviated. So you can write a point here. Deviated, but that angle is less than 1 degree. All these are observations, not that much difficult, we can remember. So 0.14 of the total alpha particles when deviated. Okay. So with how much angle? They calculated this angle also. How to calculate, we'll see. Okay. So they calculated that angle also and they said those are less than 1 degree. Very less. Somewhere around here, or here. Right? So now out of one alpha particle, out of how many alpha particles? 8,000 alpha particles deviated greater than 1 degree. Okay, so little more. Greater than 1 degree they deviated. Next. Right? So 1 out of 8,000 alpha particles deviated greater than 1 degree. Greater than what? 1 degree. Next. 1 out of 10 to the power 6 alpha particles deviated, which is greater than 90 degrees. These, according to your different books, they write differently, but very less try to understand. So if you open SCR, this count is different. So if you open NCR, this count is different. Don't worry about that. You have to understand very less amount of the things bent and deviated, right? So here 0.14 of the total alpha particles deviated, which is very less. Now 1 out of 8,000 alpha particles deviated, but that deviation will be greater than 1. Next, 1 out of 10 to the power 6 alpha particles when deviated, but it is greater than 90 degrees. Very less, try to understand it, very less. And some questions they will write it as, here it is greater than 1, here 1 out of 8,000 they deviated by 90 degrees, and 1 out of 10 to the power 6 alpha particles is greater than 90 degrees. Or 180 degrees also they can give. 180 in the sense what went and it came back. Right? Different books they wrote differently, but what you have to understand is very less in number it is deviated. Instead of writing all these three, you can write only 1 point. Very less amount of alpha particles deviated while passing through the gold foil. Clear about that? While passing through the gold foil, very less amount of alpha particles went deviated. Right? So instead of all these 3 points, is that clear? So this less than 1, greater than 1 or greater than 90, it depends on the author. So no one has seen exactly, right? So it depends. Now, try to write. Okay? Right? Now. So instead of all the 3 points, I write very less alpha particles, very less in number of alpha particles when deviated. When undeviated, most of the alpha particles. When undeviated, very less in number when deviated. Right? So in that 1 of 8,000, 1 of 10 to the power 6, and now very small, very less in number. It might be 1 in maybe 10 to the power 10 number of alpha particles. What happened? See now, 1 alpha particle came. I'll draw the diagram later, okay, after these observations. So 1 alpha particle came. This is the nucleus, assume. This is the atom, and this is nucleus. Very small, right? So alpha particle came, and distance is more, right? So it went straight. Okay. So less distance I can say. So this is positive and this is also positive, repulsive force. Oh, very good. So now one alpha particle is coming dead straight towards the nucleus. What will happen? It will come towards and later on it will move up, retraces back. Why? This is also positive, nucleus is also positive. So when then repulsive forces are there. So at a particular point, what will happen? It will move away. So chances are there, the sum of the alpha particles, it can retraces its path back. So 1 out of might be 10 to the power 8 or 10 to the power 10 number of alpha particles, it is possible. So 1 out of 8,000, chances are there are reflected back greater than 90 degrees, sometimes they will write, or greater than 1 degree in the sense, it might be equals to 90 degree also, right? So now 1 in that, so will be retraces back. So how we can calculate that? We have a formula. How we can calculate that, we'll see. Now first we will complete these observations and we will see how we can calculate that. Right. So most of the alpha particles went undeviated. So with that, most of the alpha particles went undeviated. With that, what Rutherford and his colleagues came to the conclusion that most of the atom is empty. Right? So most of the space in the atom is empty. So what he came to conclusion, most of the space in the atom is empty. Right? So how the atom will be? Nucleus, and this is the atom. So what they finally concluded, apart from this nucleus, here whatever the space is there, they consider it as empty. Electrons will revolving around the orbits, okay, but most of the things they consider it as empty space. So most of the space in the atoms are empty. Most of the space in the atoms they consider it as empty. So now, try to understand, very important. Now, how many alpha particles are deviated? So, how many alpha particles are deviated by an angle theta? How many alpha particles deviated by an angle theta? This theta we call as scattering angle. This theta we call as what? We call as scattering angle. We call it as scattering angle. Clear? So how many number of alpha particles deviated by an angle theta? It depends on number of things. So try to remember the formula. Derivations, I think in atomic physics, not that much important. If you go for the higher levels in physics, higher studies in physics, then we can discuss. Right now, if I teach, that will be waste of time. So how many number of alpha particles? See, n of theta is nothing but number of alpha particles deviated by an angle theta. I'll write everything. So n of theta is nothing but number of alpha particles deviated by an angle theta. Depends on number of alpha particles striking ni. Number of alpha particles striking the surface, or how many number of alpha particles we projected, and this is what number of atoms present in that gold foil per unit volume. So now, if I am sending 1,000 number of alpha particles, now it depends on how many atoms are there per unit volume, right? And these 10,000 alpha particles went per unit volume. In the unit volume, how many atoms are there? If atoms are less, then deviations will be very less. If atoms are more, deviations, understanding the point. If atoms are more in per unit volume, number of atoms are more, then deviations will be more. If atoms are less, further deviations will be less. So it depends on n. What is n? Number of atoms per unit volume of what? Of alpha particles or for the gold foil? The gold foil. And it depends on the thickness of the gold foil. Thickness of the gold foil, I said only one atom layer should be there. That thickness also considerable. So thickness, and it depends on some constants now. It depends on the atomic number, square of the atomic number, and charge to the power 4 divided by, right? So divided by constant 4 pi epsilon naught square, or else we can write it as k square also. So 1 by 4 pi epsilon naught we know it as k according to electrostatics. So k square also you can write, or like this also you can write. So it will be like 2r square, right? So it will be 2r square kinetic energy of the alpha particle square, right? And one more thing, sine to the power 4 times of theta by 2. Okay. Some questions they won't consider this, but these are also important. So 2r square kinetic energy alpha particle square and sine to the power 4 theta by 2. So according to your level, your board level or your competitive levels. So instead of remembering everything here, so most of the questions will be dependent on this atomic number and as well as this angle, sine to the power 4 theta by 2. So if you remember these two, I think most of the questions we can do. Number of alpha particles deviated by an angle theta depends on the square of the atomic number and depends on inversely proportional to sine to the power 4 times of theta by 2. Most of the questions will get from these formulas, but if you remember all the things, will be better. So try to write all the things now. Try to write. So what is the thing? So n of theta. What is n of theta? What is n of theta? Number of alpha particles deviated by an angle theta. First, number of alpha particles deviated by an angle theta. Deviated by an angle theta. What is Ni? Total number of alpha particles. Total number of alpha particles. What is N? Number of atoms per unit volume of the gold foil. Next, P, thickness, and E we know charge, and this is constant we know. And what is R? What is R? It is the distance. Important this one. It is the distance between gold foil. It is the distance between gold foil to the screen. Radius. Right? So after striking, this is the radius, right? So how much distance they deviated or they scattered. So R is nothing but the distance between the gold foil to the screen. I think remaining things no need to write. So kinetic energy alpha, what do you mean by that? Kinetic energy of the alpha particles, square of that. Right. So sine to the power 4 theta by 2. What is theta here? Theta is nothing but scattering angle. How much it is scattered? How much it is scattered? Clear about this? Try to understand the story. I'll give a question. Start doing a question on this. So derivation is there, but directly I didn't write. Derivation is there, but according to your level, it's not that much important. Telling this formula is also two more things according to your NCERT. This formula is not there, but we are studying everything when you study it, right? So derivation it will take more time and not your level. Don't worry about that. So at least try to remember these two. What is that? It depends on the atomic number and it depends on the sine to the power 4 times of theta by 2. Question will be like this. Simple questions will come from modern physics. Assume, okay, 2000 alpha particles. Question: assume 2000 alpha particles deviated by an angle. Clear? 2000 alpha particles deviated by an angle 30 degrees or 60 degrees. right? So 2000 out of how many I don't know, more alpha particles we projected, and what I have seen on the screen is 2000 alpha particles scattered. So scattered to an angle of 60 degrees. Scattered to an angle of how much? 60 degrees. Now find the number of alpha particles scattered to an angle 30 degrees. Understood? So 2000 alpha particles bent, they deflected by an angle 60 degrees. Now find the number of alpha particles deviated to 30 degrees. Relation is there. So out of 60 degrees, so out of the total number of alpha particles, 2000 deviated by 60 degrees. Okay. Then how many deviated by 30 degrees? See. So remaining things I didn't give. Remaining things kept constant. Two cases are there, remaining things I kept constant, so I can write directly n of theta 1 divided by n of theta 2, which is equals to sine to the power 4 theta 2 by 2 divided by sine to the power 4 theta 1 divided by 2. Right? So we know three unknowns, we have to calculate the fourth one. Simple. Now the question will be like this with respect to atomic number. Now we used gold foil. Atomic number of gold foil. What is that? Atomic number. So what is the atomic number of gold foil? 79. Right? So atomic number of gold foil 79. So generally we use that only. We won't use any other things here. But for example, if I change the material what I used there, so atomic number changes. So number of alpha particles, how many they are deviating, that will be changes, right? So we can compare the things with the material also. Instead of gold foil, I use silver foil. So how many number of alpha particles deviate? It depends on what? It depends on the atomic number. Clear about the things? So now you can substitute here, substitute and try. Next observation. Right? So next observation. Next observation. Try to think about the next observation. What they made. Okay? So most of the alpha particles went and they undeviated. Only some of the particles they retraced back. In the sense what? So next observation. Try to write the number. I forgot. Okay. So observation only. Observation of the team. Right. So most of the alpha particles went undeviated. Only a small number which is deviated and which is retraced back. In the sense, what he concluded is okay. Something is there at the center of the atom. Something is there at the center of the atom which is of positive charge. So what he finally observed and concluded that at the center of the atom, all the things I think we know, but we have to study again because now we are not in 2020. Assume we are in 1911. We are at 1911 and we are studying all the things. So if you are in 2020, sir, what nonsense you are talking? We know about that nucleus is positive. Yes, we know that. But whatever the observations did by the team, we have to study. So that's why we have to go back to 1911 and we have to study about the things. Right? So what he finally concluded at the center of the atom, a positively charged particle is there. A positively charged particle is present. Okay, so at the center of the atom, a positively charged particle is present. Finally concluded that. Okay, so a positively charged particle is there at the center. Now he named it as nucleus. Rutherford named that particle as nucleus. Named that particle as what? As nucleus. Clear about the point? So at the center of the atom, a positively charged particle is there, and the Rutherford named it as nucleus, and he discovered the nucleus from them, right? So who discovered nucleus? We know Rutherford discovered the nucleus. So how he discovered? Based on this experiment done by the team, right? Clear about the point? So this is the thing observed by the Rutherford. Now next observation. Next observation. So again we will go back to the things and we will study about the thing, right? Is that clear up to here? So Rutherford discovered the nucleus. Now, okay, my nucleus is there. Okay, so you want to know the radius of the nucleus and the radius of the atom. Radius of the atom, before that only he discovered, he said it's around 10 to the power minus 10, right? Around meters. Now, what will happen? What will be the radius of the nucleus? What he said is, see, he did another experiment again, not that much difficult. So that experiment we call it as the distance of closest approach, right? The next heading. Next heading, what is that? It's the distance of closest approach. So continuation of the Rutherford's model. So he did many things. Right? So next topic is about the distance of closest approach done by again Rutherford. The distance of closest approach done by again Rutherford. So tell me, so how he did in the sense, so he considered again go for an atom. So try to understand. He considered an atom again. Consider. Okay, atom, and inside he placed in the sense inside of the atom nucleus will be there. What he placed? Nonsense. So nucleus, and this is what? This is atom. So this is atom, and this is nucleus. We know, right? So now what he did is, so he considered an alpha particle, fast moving alpha particle. From the source it is coming from somewhere. So it is moving, right? It is moving with some speed v. This alpha particle. When. So what will happen actually while going? Retraces back to discuss the 1 out of 10 to the power 6 or 10 to the power 8. What will happen? It will retraces back. Why it will retrace back? In the sense, that particular alpha particle will go straight towards the nucleus and about to collide that nucleus. But collision, not possible. Not possible exactly. Possibility will be there. It depends on the energy of the alpha particle. So I can't tell it is not possible, right? So who decide? Who you are to decide, right? So possibility will be there. If more energy I give, then chances are that it can collide. So it depends on the energy of the alpha particle, right? So now here it is not colliding. So I gave some particular amount of energy to the alpha particle such that it can't collide the nucleus. If it is beyond that, then definitely it will collide, right? So now the alpha particle I gave some energy. So now it went. So what will happen to the energy of the alpha particle? Decreases or increases? See, while going. See, distance decrease. So what will happen to the repulsive forces? We know F is inversely proportional to the square of the distance. If distance decreases, repulsive force increases. Distance decreases, repulsive force increases. So finally, up to a certain extent, it can come, and later on, what will happen? It will move back. The distance from the nucleus, to the alpha particle, we call it as the distance of closest approach. Represented down. Right? What is that? It is the minimum distance between. Right? So definition. It is the minimum distance between alpha particle and nucleus of the atom. If you can right? Or else you can leave, right? So it is the minimum distance between the alpha particle and the nucleus. So initially it is having some energy. Now it is moving towards. What will happen to the energy? Increases or increases? Decreases. At a particular instant of time, what will happen? The kinetic energy converted to potential energy, and then what will happen? It will move back again. Now again, potential energy converted to kinetic energy. Why all these things are happening? Only conservative forces are there. Non-conservative forces are not there. So only electrostatic force is there. Electrostatic force is a conservative force. If only conservative forces are there, then we can write energy conservation. Now what we can write? Understood the point? Only conservative forces are there. What are conservative forces? Electrostatic force, gravitational force, spring force. Right? So no springs are there. Gravitation means compared to this velocity of the alpha particles, gravity won't affect. So I think this point you have to understand. Sir, gravitational force also chance will be there. No nucleus somewhere it is, alpha particles somewhere it is going. So gravity should act. Compared to the speed of the alpha particles, gravity is negligible. So we are not considering that gravity. Right? So now only electrostatic force exists between them. So I can write what I can write. So I can write it as conservation of energy. Right? Conservation of energy now. We can write what? Conservation of energy. What do you mean by conservation of energy? Total energy initial, which is equals to total energy final. Total energy initial and total energy final should be same. So tell me what is total energy initial? Total energy initial, alpha particle is somewhere at infinity assume. So if I see it as a system, now alpha particle is very long distance, infinite assume. So only kinetic energy of the alpha particle will be there. So kinetic energy of the alpha particle is nothing but initial. Potential energy, I said alpha particle is at infinite distance. Potential energy formula K Q1 Q2 divided by R, we studied in electrostatics, right? So R now I said it as infinite. So it will be equals to 0. So what is initial potential energy? Will be 0. This is potential energy, kinetic energy, which is equals to now finally it came to point B. From infinity, alpha particle moving with the speed v. So kinetic energy of the alpha particle at point B. So kinetic energy of the alpha particle is 0. Sir, it came to rest here. So alpha particle came to rest at point B. So kinetic energy of the alpha particle is 0 plus. Now whatever the kinetic energy that the alpha particle is having, converted to potential energy between these two. From the nucleus to the alpha particle. So potential energy formula we know. What is that? It is K Q1 Q2 by R. So tell me what is Q1? What is Q1? Charge of the alpha particle. So yesterday I think I said, what is the charge of alpha particle? 2 times of the charge of positive charged particles, right? 2e. 2e is what? Charge of the alpha particle. Can I write? Charge of alpha particle, which is plus 2e. Next, charge of nucleus, positive or negative? Charge of nucleus, positive or negative? Positive. What is the charge of the nucleus? Positive charge, and it depends on the atomic number of the atom. It depends on the atomic number. So it will be plus Z times of E. Right? So charge of the alpha particle 2e and the charge of the nucleus is plus Ze. Plus Ze. Clear about that? Now potential energy is K times of 2e into Ze divided by, what is the distance between the alpha particle and the nucleus? It is R0. So this is the final, this is initial potential energy, this will be final potential energy. So what I can write now? It is K into 2, right? 2 KZ E square divided by R0. Clear about the point? So now we have to calculate this distance of the closest approach. Now we can equate these two. So tell me, can I write kinetic energy of alpha, which is equals to 2 KZ E square divided by R0. So where which is equals to 2kZe square divided by kinetic energy of alpha. So this we call as the distance of closest approach. You need to write again. So if you want, you can write. This is nothing but the distance of closest approach. So kinetic energy of the alpha particle, it depends on what? It depends on the kinetic energy of the alpha particle. It depends on two constant, k constant, e constant. It depends on the atomic number of the atom. Right? So R naught depends on Z and R naught depends on the kinetic energy of the alpha particle. So that's why I said all chances are not there that alpha particle collides the nucleus. Yes, there. When see, if kinetic energy of the alpha particle increases, R naught value decreases. If kinetic energy is more, then what will happen? This R naught value decreases. If R naught value is 0, then what will happen? That alpha particle collides with the nucleus beyond a particular value of the energy given to the alpha particle. Right? Clear about this? Distance of closest approach, you have to write the conservation of energy. Apart from that, nothing. So why only conservation of energy? Only electrostatic force is there. Electrostatic force is a conservative force. So we can write like this. So potential energy initial and the potential energy final is this one. Kinetic energy final is 0. So if you want, you can write kinetic energy initial is nothing but kinetic energy of alpha particle. Kinetic energy final equals to 0. Why? Because alpha particle will come to rest. Right? Charges important. Right? Clear about the things. So this is about the distance of closest approach. Happy with the things? Right. So now, sir, what about the radius of nucleus? Again, we will go to the observations. Sir, you calculated distance of the closest approach, okay? Then what about the radius of the nucleus? He finally, by doing some experiments, he concluded that compared to the distance of closest approach, very important point, make a note, okay? So compared to the distance of closest approach, the radius of the nucleus should be less. Compared to the distance of the closest approach, radius of the nucleus should be less. Radius of the nucleus should be less than, so the distance of closest approach. Radius of the nucleus is less than what? The distance of closest approach should be less. So how we can tell it should be less? Take a question again. So start doing. Then we can compare the things. So now consider a gold foil. Start doing a question. Clear about the things after now what we are doing. So we are discussing about the Rutherford's experiment, right? So we are discussing about the Rutherford's experiment. So now we are calculating what? The distance of the closest approach, right? We are discussing, we are trying to calculate the distance of the closest approach. Okay. For that, what I am doing, I considered a gold foil. So gold nucleus I considered. So what is the atomic number? 79. We know. What you want now? Kinetic energy of the alpha particle. I have sent an alpha particle with an energy of 24.6 mega electron volt. Clear? So I considered a nucleus and the gold foil. I took that and I placed it. So atomic number we know. And I have sent an alpha particle with a speed of 24.6 mega electron volt. Is that okay? Mega electron volt. Mega in the sense 10 to the power 6 already we know, right? So 24.6 mega electron volt. Find question. Find the distance of closest approach. Start. Find the distance of the closest approach. Clear about the point Z? In the sense the nucleus of the gold I considered. And I sent an alpha particle with a speed of 24.6 mega electron volt. Now I am trying to calculate the distance of the closest approach. That time we will get something, right? So the radius of the nucleus will be less than this what distance of the closest approach. That is the thing. Oh, might be approximately same also. Might be it can be very much less, right? So what will happen? R naught will go and it will strike the nucleus. I said beyond something it is possible. Beyond something, some kinetic energy it is possible. Now calculate R naught and we can compare. So what is the radius of the nucleus? Now we know what is the radius of the nucleus. It is around 10 to the power minus 15 to 10 to the power minus 14 or 16 meters approx. Or approx 10 to the power minus 15 is exactly you can see in all the books. What is the radius of the nucleus? Around 10 to the power minus 15 meters. Around 10 to the power minus 15 in meters. Now, how will we get that? How will we get that? So, substitute all the values, I think we can get. So, what is R naught? Which is equals to 2 times of K value we know 9 into 10 to the power 9 into, so Z value we know 79 and E value we know. So, how much is E? It is charge, right? So it is charge, it is around 1.6 into 10 to the power minus 19 whole square divided by, so energy of the alpha particle I gave as 24.6 into 10 to the power 6 into electron volt, convert into joules, it will be 1.6 into 10 to the power minus 19. This conversion I said in dual lecture. So 1 electron volt in joules, it will be 1.6 into 10 to the power minus 19. So that's why 24.6 in joules, I can write as 24.6 into 10 to the power 6 into 1.6 into 10 to the power minus 19. This value, if you calculate, I think will be around approximate 10 to the power minus 15 meters only will get. Yes or no? Try to calculate approximately some 9 point something. I too didn't remember exactly. Try to calculate 9.4 into 10 to the power minus 15 meters approx we will get, I think. So standard value, that's it. Okay. So 10 to the power minus 15 into 9.4. Right? So what we can understand now? This distance of closest approach concept he developed to calculate the radius of the nucleus. Now the radius of the nucleus also should be in the order of 10 to the power minus 15. So that's why he gave the radius of the nucleus as 10 to the power minus 15. Not exactly, but some variations are there, but in the order of 10 to the power minus 15. So again it depends on atomic numbers and mass numbers and all. We'll see in the nucleus. R equals to R naught into 8 to the power 1 by 3 is the exact formula to calculate the radius of the nucleus. It depends on mass numbers and all. We'll see later on. But up to now, what I said, we are not in 2020, we are in 1911. So there they are doing some experiments on this and they are trying to develop one new thing. Right? So according to Rutherford, he said finally, this is the particular value. Why I can say only 24.6? Why not beyond this value? Rutherford, what he did, beyond this value, if it is 25, 26 or 27, what happened is that alpha particle collided with the nucleus. So at a particular value which is not collided, minimum thing we got, that is approx this energy given to the alpha particle. So that's why this we can tell it as the minimum distance. If that is the minimum distance, the radius of the nucleus also approximately nearer to this value he came to the conclusion and he gave the radius of the nucleus in the order of the same thing. That is the story behind the radius of the nucleus, how he gave that value. Right? Here stories will be more, not like other chapters like everything will be derivations and we are trying to calculate that. No, we have to think a little on what they did at that time and trying to tell the same. Right? Clear about this point? So this is about the distance of the closest approach, and why we studied this concept is to calculate the radius of the nucleus. To calculate the radius of the nucleus. Now the alpha particle strikes the nucleus or not? Yes. Beyond a certain limit of the energy, if we give to the alpha particle, then definitely what will happen? The alpha particle can strike the nucleus. Chances will be there. Right? Clear about the point? Okay. So next concept, what he did? Next concept. Again, Rutherford, very big story. He did very big things, right? So next concept is about impact parameter. All the things up to now what we are studying relevant to that experiment only. Yes or no? And we are not going out of that alpha ray scattering experiment. We are in the alpha ray scattering experiment, and we are thinking two more concepts. All the observations, all the things comes under the observations of alpha ray scattering experiment. Yes or no? We didn't come back of, we didn't go out of alpha ray scattering experiment. We are in the alpha ray scattering experiment, and we are trying to calculate, trying to think all the things. Right. So one more thing in the experiment. What is that? It is impact parameter. What do you mean by this? Try to understand the diagram first. So again, I consider an atom, and at the center, nucleus. At the center, nucleus. Right. So now, before going to impact parameter, leave the nonsense. We'll see later. Try to come to the story. So now, the center of the nucleus, I am drawing the dotted lines. Right, from the center. No alpha particle is there. If alpha particle is there on this dotted lines, what will happen? It will retraces its path. We know that, right? So now what I am doing, right? So cancel the alpha particle, right? With some speed it is, what will happen? What will happen? Okay, so what will happen? Same distance, another alpha particle. What will happen? One more, one, give the names, one, same distance, so 1 dash. Another alpha particle. Up to there I am drawing, then we have to think about it, okay? So another, almost same distance. So 2 dash. This is also an alpha particle, this is also an alpha particle. All are alpha particles. Now why to leave this dotted line also? Another alpha particle, 3. So what will happen? Think what will happen. Positive charged particle 1 and 1 dash. See, from the center of the, what I am trying to tell, concentrate here. Okay, from the center of the nucleus. What about the particle? It's at more distance, right? From the center of the nucleus, the first alpha particle is at more distance. If there is more distance, then what will happen? The deflection will be less. Try to think about that. If the distance is more, we know that. Up to now we discussed that only, right? So if it is nearer to the alpha particle, then what will happen? Scattering angle will be more. So n of theta is inversely proportional to some nonsense. In the sense what? So angle will be more when the number of, that is according to the number of alpha particles. Now we are not discussing about the number of alpha particles, we are discussing about the distance. Now first particle is at more distance. So if distance is more, what will be the electrostatic force? Distance is more, electrostatic force is less. So repulsive force will be less. Getting the point? If distance is more, electrostatic force will be less. Then scattering angle also will be less. Concept. If distance is more from the center, so electrostatic force will be less. If electrostatic force is less, then scattering angle also will be less. Now, how they will scatter? See. Right? So, where to draw the dotted lines? Right? So now this angle we call as scattering angle. Right? It went like that. Less. Why less? Distance is more. Then what about this 1 dash? Same distance. Then same distance. Right? Same distance, and the scattering angle also should be same. Right? So what is that angle? That angle will be theta. Same angles. Why? Because same distance. Clear about the point? Next. Second one. See the second one? Second particle is coming in this direction. Right. In. Right? So now its distance decreases. See, distance reduces, electrostatic force increases, so scattering angle also increases. Yes or no? So distance decreases, force increases, so scattering angle also increases. So how it will scatter? Repulsive force. See, strong repulsive forces will be there. Right? Strong repulsive forces will be there. So now scattering angle more or not? Increased. Now same distance again. Suppose 2 dash. Same distance. Now what will happen again? What will happen? So the same scattering angle again. See same angles. So now third one. See third one. What is the scattering angle? So it will go and again it will be retraced back. It will be what? It will be retraced back. It will be retraced back. What is the scattering angle? 180 degrees. Scattering angle 180 degrees. This is about, now you have to think about the impact parameter. Now concentrate on the impact parameter. What do you mean by this? What happened here? See, based on that relations, and I will write a point, try to understand. Impact parameter is represented by B again. Again, derivation is there. We have to apply conservation of energy and all. But according to your NCERT or the syllabus, so that derivation is not there. Directly we are concentrating on the formula. Impact parameter, which is equals to k times of z e square cot theta by 2 divided by kinetic energy of the alpha particle. Okay? Clear about the thing? V equals to k z e square cot theta by 2 divided by kinetic energy of the alpha particle. Now, for all the particles, just I have given the formula. First, you have to know about what is impact parameter. I didn't tell that. Just here, we have seen the scattering angles and all. What do you mean by impact parameter is? Impact parameter is nothing but it is the perpendicular distance. It is the perpendicular distance. Perpendicular distance between what and what? Between the velocity vector. Between the velocity vector. Between what and what? Between the velocity vector. Between the velocity vector from. Between the velocity vector from where? From the center of the nucleus. From the center of the nucleus. Center of the nucleus in the sense we have drawn the dotted lines. See, it is a perpendicular distance between the velocity vector from the center of the nucleus. Center of the nucleus in the sense, see, we have drawn the dotted lines, black color dotted lines. So that black color dotted lines represents the center of the nucleus. See this line. Now, what is the impact parameter? Impact parameter. If I consider for the first particle, this distance is nothing but impact parameter. See, perpendicular distance between what and what? Velocity vector in the sense particle is going in this direction. In the sense velocity vector Velocity is a vector, we know. So that direction is this one, and perpendicular distance between what and what? Between the distance from the center of the nucleus to the velocity vector. Distance between the velocity vector from the center of the nucleus distance. This we call as impact parameter. Clear about that? Now, how we can calculate that impact? This is just the last one you have to understand like this only. If you want to get more feel, I have to derive this. That will take, we can derive, but it will take more than 1 hour or so, which is not there in mains or advanced syllabus also. Direct we can write like this. So we can derive, we can waste more time, but not required. Okay. So B, which is equals to kz square cot theta divided by what? Kinetic energy of alpha particle. Now what is B? Perpendicular distance. From the center you have to draw a line and you have to see the alpha particle in which distance it is going. That distance we call as impact parameter. Now we have to discuss more about this. So can we discuss? Is that okay about the points? Can I rub the things? Right. Right? So what is the formula? It is B, which is equals to kz square cot theta by 2 divided by kinetic energy of alpha. Case 1. Case 1. Case 1. Right. So first case. We'll discuss about everything about this impact parameter. See now. Case 1. If B is more, try to write the points, okay? If you are comfortable like this, you can write like this, or if B is more, or if the distance between the center of the nucleus and the alpha, the velocity vector of the alpha particle is more, if you want to write a proper sentence. Or else, if B is more, right? So I am maintaining K constant, we know, maintaining the same nucleus. So Z is also constant, charge constant, kinetic energy of all the alpha particles also I maintain the same. So this is also constant. Now who is variable? Getting the point? If B increases or B decreases by maintaining the same kinetic energy of the alpha particles and the same nucleus I consider, but who will vary? If B varies, scattering angle. See, theta varied or not? Theta is not same, theta varied. In the sense, if B increases, all the things are constants. So I can write B is directly proportional to cot theta by 2. If B increases, cot theta by 2 increases. If B increases, cot theta by 2 increases. Clear? If B increases, cot theta by 2 increases. If B increases, cot theta by 2 increases. Now, if cot theta by 2 increases, cot, not tan. Tan 0, 0, tan 90 infinity. From 0 to 90, tan value increases. Cot value decreases. Getting the point? Is that clear? Tan value from 0 to 90 increases. Cot value from 0 to 90 decreases. Now see, cot theta by 2 increases. Then what will happen to theta? Getting the point? What will happen to theta? Decreases. This is cot, not tan. Some confusions, right? So if B increases, cot theta by 2 increases, right? If cot theta by 2 is increasing, continuation. Cot theta by 2 is increasing, then what will happen to that scattering angle? Decrease. Why decreases? We will do a question later. So try to see here. B is increasing. See, initially this is the center and second one. Scattering angle is more. Now B increased. What happened to scattering angle? Decreases. I have written here. Cot theta by 2 increases. But what will happen to theta? Decreases. Next, case 2. So I think you can write. If B decreases, what will happen? Cot theta by 2 decreases. Directly proportional. If cot theta by 2 decreases, then cot theta by 2 decreases, then what will happen to theta? Increases. What will happen to theta? B is decreasing. If B decreases, cot theta by 2 decreases. If cot theta by 2 decreases, what happens to theta? Increases. Now I think you can understand case 3. If B equals to 0, start doing. If B equals to 0, find theta. If V equals to 0, find theta. Question. If V equals to 0, find theta. Right? Visible? Right. So if V is 0, find theta by 2. Now come to the concept V 0. All these functions will go that side 0. So then I can write cot theta by 2 also will be equals to 0. Right? Cot theta by 2 will be 0. When cot theta by 2 will be 0. Yes? Cot inverse of 0. When cot will be 0. Tan 0 will be 0. Tan 90 will be infinity. Now reverse. Cot when it will be 0. Cot 90 will be 0. So it is equals to 90 degrees. Now what is theta? 180 degrees. Now I think you understood why I have written if theta by 2 increases, why theta decreases. See here, B0, cot theta by 2, 0. Theta by 2 is 90, cot inverse of 0, 90. So where theta is 180. See 180 went straight and it replaces the back. What is the angle deviated? 180 degrees. So what is the scattering angle here? At the third situation, 180 degrees. So these three cases you have to understand. Their impact parameters, all the Rutherford things will be easy for you. Still Rutherford model is there. I didn't tell the drawbacks. I didn't calculate the Rutherford's atomic model. Right? So this alpha ray scattering experiment is done. So whatever the observations are there, whatever the conclusions are there, what he made, I think everything we did. Now in the next class again Rutherford, but Rutherford atomic model we will discuss and we will see the disadvantages and what he didn't explain and who explained that. We will see the next class. Okay, thank you. Bye.